So suppose the claim is made that the eye color and the type of pet a person owns are related to each other, associated in some way. Let's say blue eyes, not blue, and let's say two pets, two kinds, cats and dogs. So I'm going to create a table. See, that's the cool. So 34, 46, 31, 49. So I go and survey people. I looked at people with blue eyes and I asked them, well, what type of pet do you have? They said, I have a cat. Then I looked at, people with blue eyes and I asked them, what type of pet do you have? They said, I have a dog. So we got that information from a survey. And in total, how many people did we observe? Or how do we come up with that number? We just add all of them together. So 34 plus 46, 80, and 80 here also. So in total, we have 160. Yes. And now, this table is what we call a contingency table. What does contingent mean? Contingent means conditioned on something. It's a condition, contingent on, you're making a condition on something. So we want to, or we're going to determine association using conditional probabilities. How do we do that? We're going to come up with something called row total. And column total. So row total, we're simply going to add those two values. That's going to give me 80. Same here, if I add those two, I will get 80. Similar manner, column totals, if I add those two, I will get 65. And if I add those two, I'll get 95. Yes. So if I add the totals across the rows, I'll get the column total. Across columns, I'll get the row total. Good so far? Now, we want to find something called marginal probability. We have two variables. One, the first variable, well, the type of eye color. The other variable is the pet that someone owns, so the type of pet. So I'm going to come up with a marginal probability for the type of pet. Then I'm going to come up with a marginal probability for eye color. The type of pet has two levels. One is cats, the other dogs. And we have defined corresponding probabilities. PR stands for the probability. So if someone asks you, well, what is the probability a randomly chosen person would own a cat? What would your answer be?
65 over 160.
65 divided by 160. What is the probability that someone would own a dog at random? If you pick a pet, 95 divided by 160. Let's get decimal values for both. You can use a calculator and tell me what you get. 4 decimal places. So if I picked a person at random, the probability the person would own a cat is 40.63%. Probability that a randomly selected person would own a dog is 59.38%. That's the marginal probability for the type of pet. In a similar manner, we can find the marginal probability for I column. What are the two levels we have? We have blue eyes and not blue. So how do we find the probability that a randomly selected person would have blue eyes?
$80 over 160.
80 over 160, which is 0.5. So according to this sample, whether a person has blue eyes or not blue eyes, it's a 50-50 chance based on this sample. And I don't think realistically that is the case. So we got marginal probabilities. Now we want to find the chances that they would happen together. What are the chances that a person would have blue eyes and has cats, blue eyes and has dogs, not blue and has cats, not blue and has dogs? Joint probability. So how do we find the joint probability? We take each value and divide by the total. So 34 divided by 160, 46 divided by 160, 31 over 160, 49 over 160. Does that make sense? So let's find those 4 values, the joint probabilities. Going to write the joint probabilities over here. Right. 34 over 160.
21.21.
Okay. 2875.
1938.
Okay.
And 3063.
Those are all the joint probabilities. The reason why I'm doing these is to know the difference, is for you to know the difference between a marginal probability and a joint probability. Here, based on this sample, if I randomly pick a person, what is the probability that person will have a cut of 40.63%? We're just going to look at people who have pets. It would be silly for me to make this inference for people who don't have pets. That'd be ridiculous. So if someone has pets, what is the probability that they would have dogs? 59.38%. Likewise, at random, if I picked a person, what are the chances that they would have blue eyes? 50%, not blue, any other color, 50%. So we are looking at the variables and their levels individually. The interpretation here, what are the chances that we have blue eyes? We pick a person, the person has blue eyes and owns or has cats. What are the chances of that? Or what is the probability of that? If I randomly picked one of you, what are the chances that that person will have blue eyes and has a cat? 21.25%. What are the chances that if I picked a person that they would have eye color other than blue and owns a dog? 30.63%. See the difference in interpretation? Yes. Now, neither of those by itself is going to give us a conclusion on whether type of pet and eye color are associated. Because here we are looking at eye color and type of pet separately. Here we are looking at a joint probability of them happening together. So if we want to determine if there is an association, we need what we call a conditional probability. So we can create a table of conditional probabilities. But before I do that, let me ask you this question. Just by looking at that table, do you believe that there is an association between the type of pet and eye color?
Being like just one out of the two or individually?
I mean, just by looking at the table, do you believe that there would be an association? Why not? You say no, but why not?
Because the numbers are so close together when looking at like cats, like the numbers of cats for blue eyes and not blue eyes are so close together and similar for dogs.
What's your name?
Aaron.
Aaron. So Aaron says, well, the numbers are very close to each other, right?
Yeah.
But go ahead.
And another thing is, well, for both instances, whether they're blue eyes or not, dogs just may be more popular amongst the pet owners, like on both cases.
Oh, over here.
Yeah, like dogs.
Comparatively.
Yeah, because dogs are higher on both for both.
True, but we're sort of connecting the two together, right? So your argument simply states that dogs are more popular than cats.
Yeah.
But I want to connect them together. So Aaron mentioned the counts are very close to each other, whether you have blue eyes or not. 34 here, 31 there. 21.25%, 19.38%. But this is quite subjective. Do you agree? It's not objective at all, because one may not say, oh, well, I may consider going from 34 to 31 to be one and the same. You may say they are different, significantly different. So that is the purpose of the test that we're about to do. But a probability-based inference can be made using conditional probabilities. So what is a conditional probability? If I pick a person with blue eyes, conditionally, in other words, I'm making sure that the person has blue eyes. Over here, my interpretation was, I don't care what color eyes you have. If I picked a person, what are the chances that they would have blue eyes and have cuts? But now I'm going to condition on the fact that the person has blue eyes. So given the fact someone has blue eyes, what are the chances that they?
I mean, you would have to do something with the percentages of the blue eyes, the cats and dogs.
So given the fact someone's got blue eyes would mean, which total should I look at? Should I look at the entire total 160? Or should I look at the 80? 80. Because I'm saying people have blue eyes. So conditioned on the fact that I have someone with blue eyes, what are the chances that they have a cut? So 34 divided by 80. 46 divided by 80. 31 divided by 80. And 49 divided by 80.
Conditional probability.
Yes.
So the other one was marginal. The other example.
Joint probabilities, the one I had earlier, marginal probabilities. This would be the table of conditional probabilities. Let's find the decimal values for each of these. 34 over 80, 46 over 80, other two. What do we get?
.575.
575. Okay.
3875.
Have to do a bit of rounding there, right?
Yeah, and 6125.
6125.
Yeah.
So we have the table of conditional probabilities. Now, in terms of events in general, if you took two events A and B, so this vertical dash simply means given, or A conditioned on B. So A given B or A conditioned on B. So if A had nothing to do with B, what would this equal to? if A had nothing to do with B, A is completely independent of B. This would equal to the probability of, take a guess. If A has nothing to do with B. B doesn't matter. Okay. How about this? A has nothing to do with B, so what would that equal to? Just the probability of A. Do you agree? Because A has nothing to do with B. So if the events are independent, if A and B are not connected at all, probability of A given B will equal probability of A. Likewise, if we have B given A, probability of B given A would just be probability of A. You don't have to do that. Let's see. We want to look at the conditional probabilities. So we want to look at probability of cats given blue eyes, dogs given blue eyes. In other words, we are conditioning on blue eyes, right? Probability that someone owns cats, conditioned on the fact that they have blue eyes. And that's exactly what I have as a table here. Do you agree? Those are the values we found. So I will have 0.4250, 0.5750. Likewise, cats conditioned on not blue, and dogs conditioned on not blue. .3875 and 0.6125. Good. Now, A, B, right? If A is independent of B, probability of cats conditioned on blue eyes must simply be equal to the probability of cats. Agree? We already found the probability of cats. That's the marginal probability. Yes? Earlier, we erased it. So what is the marginal probability of someone owning a cat?
4063.
4063. Likewise, dogs given blue eyes, dogs conditioned on blue eyes. So if I hide that, we just want to find the probability of dogs. What is the probability of dogs? 59.38. What is the probability of cats not blue? Will it change? We're still looking at probability of cats. Will it change? No, right? It's the same thing. Probability of dogs not blue, will it change? Still the probability of dogs. Good. So one of them, if you test one of the two, you know, can sort of make an argument of independence. If the type of pet has nothing to do with the color of eyes. In other words, cats does not depend on blue eyes, then this conditional probability must be equal to that value, correct? That's exactly what I wrote here. If A has nothing to do with B, we'll simply have the conditional probability of A given B equal to the probability of A. Do we agree? Correct. Let's see. Are those two equal? But are they close to each other? Yes. How about those two? They're not equal, but they are close to each other. Correct?
Yeah.
Now, how close is close enough for us to conclude that they are independent? In other words, there isn't an association. Does that make sense? Once again, this is subjective. You may say, well, numerically, that number and that number are different, but to my eye, statistically, they're probably one and the same. Even though there is a difference, they're not significantly different. Even though there is a difference, they're not significantly different. In other words, approximately they are equal to each other. So we can conclude that there is no association between eye color and the type of pet. Does that make sense? That's pretty much what we had at the very beginning, right? When I asked you the question, look at the counts and tell me if there is an association between the color of eyes, the type of pet. Aaron said, no, the numbers are close to each other. I used a similar argument, or I'm coming up with a similar argument, but here I'm using conditional probabilities. So once again, is there an association? No, there is no association between the type of pet and the color of eyes. This is subjective also, do you agree? We just went over that. Now, why should I bother about conditional probabilities? The test we're about to do in 11.2 can be done or is done using these probabilities, right? In practice, even though this is nice and all, do you really want to explain to people with all these probabilities? Or do you want to keep it simple and sweet? Simple and sweet. So this is just the theory behind that simple test that we're going to do. Does that make sense? So why are we doing the test? Because even though they seem close to each other, or even though they seem different, are they statistically different? If they are statistically different, then there is an association. Otherwise, there isn't. Good. So, gender gap in politics. So we have political party identification and gender, female, male, and three party identification, Democrat, Independent, Republican. And we want to identify the response and the explanatory variable. In other words, what would explain, or which variable would explain the other variable? So will gender explain the political party identification? identification, or will the political party identification explain gender? Which will depend on which? That is my question. Would gender depend on political party identification or the other way around? That's an easy question. Then repeat. Would your political party identification depend on gender? Or would your gender depend on political party identification?
Party depends on the political party identification will depend on it.
So the political party identification will depend on gender, right? Depending on whether you are female or male, you know, there might be a gap in your political party identification. It's not the other way around. Just because I'm Democrat doesn't mean I suddenly change into a male, right? Just because I'm an independent doesn't imply that I would suddenly change into a female. But it's the other way around because we are looking at the gender gap. Clearly, the political party will depend on the gender. So the explanatory variable is gender because gender explains the political party that a person will choose. Does that make sense? So that would be the response, and that is the explanatory variable. Part B wants you to construct a table that shows the conditional distributions of the response variable. So we want to find the probability of Democrat given female. Very similar to what I did. In my program, I had cats, dogs, just two of them, and I had blue eyes, not blue eyes. Here we have to condition Democrat, Independent, or Republican on female or male. Good. Let's go ahead and complete that conditional. Okay, so you can give me the probabilities, but before give me the probabilities, why did they only give you the row totals and did not give you the column total? They gave you these, but they didn't give you that. Any thoughts as to why?
Conditional probability, you just need, you know, the Democrat and the female or male. You just need those types of numbers.
Oh, yes, close, yes. I see what you're saying. Any other explanations?
Just need the row total, you don't need the column tables because you divide by.
Exactly. And why do we? I've got your name.
Gender.
You know, why do we divide by counts? Why?
Because it's the amount of like the females in the Democratic, it's like each party, it's not the female and male.
Right, so we are trying to condition party on the female male. So this, each of these totals will be divided by that because we are conditioning on gender. That said, I guess I can write it separately. So what do we get when we divide?
0.3543.
Okay,
4237.
okay,
2220, I
2220,
I rounded it.
okay,
2923. 4555.
25, 23.
25, 23. Okay. What do we think? Do you think that there is a connection. Gender gap and politics, the gap and politics related. In other words, if you are, your political affiliation, does it change conditioned on gender? Is there a gap between females and males?
I want to say only in the Democrats, you can see a little bit more of a difference than.
So all goes guessing, okay, maybe among Democrats, it seems to be the case, right? Because her thought process is that 6% difference, 29 to 35. If you look at the other two, 3% approximately, right? So it seems like Democrat is the only influential case where there is a gap between males and females. Females, are more likely than males. So, but once again, this is subjective. Do we agree? And we need a very absolute way of doing this.